All right, the second fundamental theorem. This is kind of a weird thing, and people have a very difficult time with this lesson. Um, so let's just go at it. It's the idea of a function that is defined with an integral. And so that's just kind of weird. So notice that the graph of f is shown to the left. So if I ask you for g of 0, well, if I'd covered up that function and said, hey, how do I find g of 0? You'd say, well, put in 0 for all the x's. So are you with me that g of 0 would be the integral from 0, I'm plugging in a 0 for that, of f of t dt, and that you should know the answer because you think, well, if your bounds are the same, well, then it's always going to be 0. And that's correct. So if we do, let's look at a different one. G of 4 is going to be the integral from 0 to 4 of f of t dt. So I'm going to have to find the areas, being that I asked you for several of them. Let's go ahead and find the areas of these triangles. Again, be careful as you do that. You know 1/2 base is 4, height is 4, so that would be 8. Again, if you like the negatives, you can plug in those negatives. This one, 1, 2, 3, 4, height of 2, so that'd be 8 divided by 2, so that would be 4. So the integral from 0 to 4, notice that I would put -8 because it's below the x-axis and my bounds are going low to high. I think in the same way, you can now do try to do 8 and 12 and see if you get the right thing. So g of 8 would be the integral from 0 to 8 of f of t. So it's all below the x-axis, so that's going to be a lot, -16. And then g of 12, well, you know that's going to be the integral from 0 to 12 of f. I have 16 that's below the x-axis, I have 4 that's above, and that would give me a value of -12. So if I went to go plot the graph of g, then I would have points of 0, 0, 8, -16, 4, -8, etc. It's just that g was defined as an integral. So if you look at it this way, when your function is defined as an integral, if you're finding g, with the letters the way they are, notice what I did to get this is the area under the curve. Okay, that's how I did that. Now, I want to put a big star in your notes, and although I wasn't too picky about it, and maybe you didn't even notice, this lower bound is a very big deal. Because if I would have said g of x is equal to the integral from 4 to x of f of t dt, well, then g of 4, let's do an easy one. If that bottom bound had been 4, then g of 4 would have been 0, not -8. So y'all, that bottom bound, when you're finding that function's value, the bottom bound is very, very important. So put a big star right here and put super important. You can't just disregard that number and just kind of let it go. Okay, now let's look at the next one. Notice with the next one, it says g prime of 0. Okay, well, okay, let's figure something out here. So what we figured out in step 1 is that g of x was the integral, I just really didn't figure this out from step 1, it was given, of f of t dt. Yes, that's the given statement. Now, if I were to actually find the derivative, if I wanted the derivative of g prime of x, that means that's the derivative of that integral. I just took the derivative of both sides, correct? Okay, well, let's work this out. If I wanted to find the derivative of this integral, think about how I would find this integral. Wouldn't you take the antiderivative? So for this notation, I'm going to call that big F. So I'm going to say that big F, is the antiderivative of little f. So big F, I take the antiderivative, I would evaluate at the top bound, and I take minus the evaluate at the bottom bound. We good with that? Okay. Well, wait a minute. If big F, is the antiderivative of little f, then that means f is the derivative of big F. So hold on. If I say, what is the derivative of big F of x? Well, that would just be little f of x. Now right here, if I evaluate the antiderivative at a constant, what am I going to get? I'm going to get a constant. So right here, won't this piece go away? So what is the derivative of g end up being? It's just f of x. Now, here's probably where you're confused. You're like, wait a minute. I don't understand why over here it has t's. You told me that this was t's and these x values along here, and now you're telling me they're x's. I know that's confusing, but they can't, up here when they define the integral, I can't use x's here, or that would be super confusing, so you'd be plugging in x's in too many places. What you have to get is that, friends, the second fundamental theorem says if you want to take the derivative of an integral, there is something that you can do. And we'll write this on the other side very specifically, but I'm doing this problem first. This is the graph of g prime. So peeps, if I ask you what is g prime of 0, well, if g prime is equal to f, aren't I just looking, this is really f of 0, and this is really f of 3, and this is really f of 4? Is it that simple? Yeah, it is. But you got to get to that part if people mess that up. If this is the graph of f, it is the graph of g prime. Literally, to get these y values, I am looking at the y values. Okay? I'm looking at the y values on g prime, which of course is equal to f. So for f of 0, my y value is 0. For 3, my y value is negative 3. For 4, my y value is negative 4. And I am literally reading those off. The next one is asking for the second derivative. Well, let's not make this harder than it is. If my graph right here is g prime, if I want the derivative, I don't want the y value at this point, I want the derivative. If this is g prime, it's asking for g double prime of 3. So isn't it saying I want the derivative at that point? Well, miraculously, these are all lines. So what I'm doing here, what I'm going to be doing, I am looking at the slope on g prime, which would be, of course, the derivative of g prime, which is g double prime, at a particular x value. So when they ask me g double prime of 3, I am looking in this point. I'm not looking at the y value. I'm saying, what is the slope of that line? Well, I can read off the graph. The good news, I can read that off. The slope of that line is negative 1. At 4, what's the derivative at 4? Well, you have a left-hand derivative not equaling the right-hand derivative. You have a sharp turn there, so that would be does not exist. And g double prime at 10, I look at this point, I don't put 1. I look at the slope of that line, which I can read off. It's up 1 over 2, and I get a value of 1/2. Now, I'm going to be honest with you. This is super popular because on AP, because, oh heavens to Betsy, look what we can do. We can combine 2 units. Sweet friends, they can ask you about second fundamental, which were these problems. And then if you have the graph of G prime, then you can answer questions about the graph of G via, oh golly, using curve sketching. So all that stuff that we did in curve sketching, and that's why they love this question, is because it combines 2 units perfectly. So you say, holy cow, where would G be increasing? Well, friends, once you made the connection that this is G prime, let me erase all these numbers because I don't want to let them confuse you when I'm doing the curve sketching part. Once you have made the connection that this is G prime, all the questions 1 through 4, we've answered them before. It's not anything new. If I gave you a graph of G prime and said, where is G increasing? I like to write my justification first. You would know that. You would say, well, G would be increasing when G prime is positive. And so here I go. Now, there's one thing that you need to star in this. Where would G be increasing? You're going to say G increasing when what? G prime is positive. Friends, this star this. The first time, if you just put when G prime, they're going to say, well, how are you answering questions about G prime? We didn't give you G prime. Remember how I said you have to defend with the derivative that's given? Well, they didn't specifically say, hey, this is a graph of G prime. You have to tell them how you know that is the graph of G prime. It does not matter. Do I write it up here on my graph? Yes. But they don't grade above a certain line. I don't care if you have it up there. You have it in your justification as well. Now, you don't have to write it every time. Once you have established that you know, so the first time I talk about G prime, I say, hey, G prime is F. From there down, I can just talk about G prime. But man, that first time, I have to put that G prime is equal to F. Now, I haven't even answered the question yet. So let me go back. Can't forget to do that. Where is G prime positive? Where on that graph do I have positive values? Well, right here. So 8 to 12. Got to actually write that. So I want you to stop the video and I want you to see if you can remember these functions, or these justifications, and get these values. So would G of X have a local extrema? Yep, it sure would. What would you be looking for? You'd be looking to see when the graph of G is changing signs. So G has a local min at x equals 8 since G prime changes negative to positive. So you can see on the graph, right here is where G prime changes from negative to positive. Where would G be concave down? G is concave down when what? When G prime is decreasing. So where is G prime decreasing? Go back on your graph. G prime is decreasing right there. So 0 to 4. Love all these connections. Super cool. Would G have any points of inflection? Well, what would you be looking for on the graph? G has a POI when G prime, what do I have to write? Goes increasing to decreasing or decreasing to increasing. So does our function do that? Yep, I go decreasing to increasing right here at 4. So x equals 4 would be a POI. Cool. Cool, cool, cool. All right, let's go to what the second fundamental actually says. Now I'm going to kind of refer back to this. Here's a point that that we did, and I'm writing this in a kind of a weird way, but hopefully it will help you understand it and remember it. So it says if you have a function, okay, an f, and again I just named this. If that is, and I have some upper bound and lower bound, whether these are constants or not, it has a derivative. If you're going to take the derivative of this function defined as an integral, y'all, I know that has a lot of letters. I promise it will make sense. And I'm going to put it in words. This is replace with the upper bound, and this of course is the derivative of the upper bound, minus, this means replace with the lower bound, and this is the derivative of the lower bound. Okay, we're not going to worry about this right now. Okay, here is what it comes down to. Okay, and again, I'm going to work out number 5 a different way. Just watch me for a second. If I were doing this, I kind of did it on the screen before, because remember how I did this whole business right here? I would take the antiderivative and plug in. Let me do that with this first one. Okay, you don't even have to write this down, but just hang with me. If I wanted to actually do this integral, I would say, okay, take the sine of t, that's the antiderivative, and evaluate it from pi over 2 to x. Do you agree? And I haven't taken the derivative, so this is just big F of x. So that would be equal to the sine of x minus the sine of pi over 2. Now let's just leave that. I know I could simplify sine of pi over 2, but I'm not going to do that. Well, the question is for f prime. Well, for f prime, if I said, hey guys, take the derivative of the sine of x, what would you say it is? You'd say, well, that's the cosine of x. Now, what is the derivative of any constant? 0. So what is the derivative? And I get cosine of x. And you go, well, that didn't take me too long. I mean, okay. And I think you would see that. Let me change this. Let's say this were 2x up there. Well, right here, when you took the derivative and you have the sine of 2x, when you replaced, and you would have the sine of 2x right here, what would be the derivative of that? Well, that would be 2 cosine of 2x, right? So if the upper bound is not just x, you would have to multiply, and that's where that 2 comes from. Okay, so you go, well then why don't I just do it that way? Well, if you can integrate this thing, then sure. I don't think you're going to like it that way. This is going to be something you can do very quickly, especially when they give you a function that you can't take the integral of. Like you have no idea, if you look at number 6, how to take the integral of natural log. Okay, it involves something called integration by parts, and you don't know how to do that, and you never will in this course. So what happens when you have to do it that way? You have to be able to understand this theorem. And although all those letters look complicated, if you understand this process, here is what it is. They're asking you the derivative of a function that's defined as an integral. You go, oh, that's that weird replace thing. I'm going to go straight to f prime of x. I am going to replace the t's with the upper bound. So cosine of x, that's replace with the upper bound, times the derivative of the upper bound. Well, what's the derivative of x? 1. Minus, if I replace with the lower bound, that would be cosine of pi over 2. Well, what's the derivative of the lower bound? That is a constant, so that would be 0. So what is f prime of x? F prime of x is the cosine of x. Now let's look at this statement, and I bet it makes sense. If your function, if the bottom bound is a constant, it doesn't matter which constant it is, do you see that this part will go away? Because if you have a constant, that derivative of the lower bound will be 0 every time. So some people just go, okay, if the bottom is a constant, then I just forget it and I just do this first part. Yes, absolutely. Okay, so let's look at number 6. Sweet friends, number 6 says, find the derivative of a function which is defined as an integral. That's when your brain should think second fundamental. It should think this thing right here. You go, all right, f prime of x. I'm going to replace, so that's ln of x plus 3x. I replace all of them. Well, I would subtract the bottom, but man, I've memorized that if the bottom is a constant, this whole part will go away. That question is over. Done. Finished. Finitoed. Let's look at number 7. Number 7 says, what's the derivative of y? Now don't get confused why that's dy dx. Actually, that shouldn't even be there, and yours is going to have it right. There we go. Yours is going to have it right. What's the derivative of this function that's defined as an integral? Well, that's really asking the same thing as this. They just wrote it in a different way. The derivative of a function defined as an integral. I'm going to replace cosine of x cubed times the derivative. So I replace the upper bound in for the t's, but I can't stop there, times what? Times the derivative of the upper bound. So that's 3x squared. So my final answer for that derivative, I'd probably put that in front, would be this. So it's more like, I don't expect you to memorize those letters up here because F, U, L, L, too many letters. Memorize the process. Replace with the upper bound times the derivative of the upper bound minus, and then do the lower bounds. So let's try number 8. Number 8 says, they're asking me for the derivative of a function defined as an integral. I think, that's easy. Second derivative, second fundamental theorem. So I replace all the t's with 4x. So I have 4x squared minus 3 times 4x. I'll just do it like that. Obviously, most of you would simplify that in your head first, but I can't stop there, times the derivative of the upper bound, which would be times 4. So what do I really have? I have 16x squared minus 12x, and I need to multiply that by 4. So f prime of x equals, what is that, 64x squared minus 48x. You know, could I do it where I actually do the integration? I actually plug in and do the first fundamental theorem and then take the derivative? Yes, I could because I know how to integrate that. But I'm telling you, this is a heck of a lot faster. And like I said, they're going to give you functions on there that you can't integrate. And so they're forcing you to do it this way. Now let's look at number 9. No big deal. Our bottom functions are not just x's, or not just constants. So let's see what I would have. I'm going to use my process. Are you ready? I'm going to replace, so 4 times 2x to the third times what? The derivative of the upper bound, minus this one. I can't just go, oh, that part's going to go away. If I plug in the 4, plug in the x, 4x cubed, the derivative of the lower bound is 1. So what do I get? If I clean that up, well, that's 4 times 8x cubed. Be careful with this. This right here is 4, nope. This right there is, wish I could rewind on this thing, but I can't. So I have 8x cubed, that's this part. I have times 2 times 4, so that's times 8. So that would be 64x cubed minus 4x cubed, and that gives me 60x cubed. And that's my derivative. On this one, again, you have it right on yours. Ignore that y, that shouldn't be there. So I have this. It's asking me the derivative of an integral, of a function defined as an integral. So I replace with the upper bound times the derivative of the upper bound. I'm going to write that just so you know I don't forget about it. Minus 2, replace with the bottom bound, times the derivative of the bottom bound. What does that give me? 2x plus 2 minus 2x. I end up getting a constant on this one, and I get the number 2. So kind of weird, but once you get it, it's not that bad. People just don't know when to use it. When do you use second fundamental theorem? When the question asks you for the derivative of an integral. That's when you need to think second fundamental theorem. All right, peace out.